This is part 3 of cosmology and space physics. In this, we're going to do Hubble's law and Big Bang, and we're going to look at Big Bang theory. So first, we have to understand the emission spectrum of distant object, increase in wavelength, and we understand their values as well. So this effect, this idea comes from Doppler effect. If you are not familiar with Doppler effect, please go check out the video. I will add the link in the description as well if you want to revisit what Doppler effect is. This effect is from O levels space physics and from A1 space physics, I think. Yeah. So Doppler effect basically just tries to tell you that if an object is moving away from you, for example, if this is where you're standing, if the object is moving away from you, then the frequency perceived by you will be lower than the actual frequency produced by the object. And this could be a sound wave. This could be an electromagnetic spectrum wave as well, from gamma up to radio. But if the object is moving towards you, then whatever frequency the object is producing, your perception of that frequency will be larger. So if the objects are moving towards you, the frequency is higher. If they're moving away from you, the frequency perceived is lower. This is primarily the Doppler effect. Now from this Doppler effect, we move towards redshift. What is redshift? Now basically what happens is that we look at the spectrum, the absorption spectrum from our own sun, which is the closest cosmic object that we have, which is emitting radiation, which is emitting light. These wavelengths are missing. This is the characteristic of our sun, right? Now, when we look at another sun or another star from another galaxy, we should get the same response. This is the basic idea. We should get the same answer. We should get the same absorption spectrum. But what happens is that we observe that these wavelengths that should be here are not here. They're slightly shifted towards this side. Now, what is the meaning of this shift? You see, for the sake of example, let's say that this wavelength from our sun, which is missing, is probably, let's say, 600 nanometers. But when we check the same wavelength, same absorption spectrum, same missing wavelength from another distant star, the same behavior is depicted, let's say, at a wavelength of 620 nanometers. And similarly, we see that all the wavelengths are actually slightly shifted away from the true nature, from the true behavior. And since they are getting closer to the red side of the spectrum, we call this as the red shift, right? Every wavelength is shifted slightly. Now, this is a red shift, okay? You can also memorize the definition as well. So first part is that we understand, or we need to understand the emission spectrum, how the emission spectrum leads to Doppler effect and leading to finally the red shift, okay? So we understand point number one. Moving on to point number two, this is the equation for that red shift. How we use this equation is, for the sake of example, let's say that the actual frequency or the actual wavelength is 600 nanometers, but the perceived frequency is 620 nanometers, right? So we use this formula as the change in frequency, right? So the change in wavelength. So this will be 620 minus 600 divided by 600, which is the true value. This will be divided with the true value. This is approximately equal to V divided by C. Now, V is the speed of the galaxy or speed of the star that is moving away from you. And C is the speed of light. Of course, this equation gives you an approximate answer or an approximation, but we look at this speed as speed of recession or the speed of moving away. Why is that the case? You see, in the Doppler effect, we understand that if the object is moving away from you, the frequency that you will perceive is going to be lower than the actual value. Now, if the frequency is lower, then from V equals to F lambda, we can say that the speed of light is constant. So let's rearrange the equation to look like this. If the perceived frequency is lower due to Doppler effect, then the wavelength will be greater, right? That's why all the wavelengths from this spectrum are going to shift towards a higher value, 600 to 620 for the sake of example. Probably this is, let's say, 500 and shifts to 550. And similarly, all the wavelengths that are missing in the emission spectrum will be shifted to a higher value. Since they are moving to a higher value, since the wavelength is increasing, we can predict that the frequency is decreasing. So we backtrack our way towards this conclusion that if the frequency is decreasing, that means that whoever is emitting this radiation our way, whoever is sending light our way, is actually moving away from us. This is the redshift. And this idea gives us the understanding, or you can say the reason or evidence for the expanding universe and the Big Bang theory. Now, what is the expanding universe? You see, if this is where we're standing, this is the Earth, we have the sample from our own sun. We know what stars should look like. We know what their spectrum should look like. Let's say there's another galaxy, Andromeda. There is another galaxy, Galaxy 2, that is certain distance away from us. And all the stars from this galaxy are sending their light or sending the radiation our way, right? Let's say this is also sending radiation our way. Now we understand that the standard response from the sun should be this one, which is this spectrum. When we analyze the spectrum coming from distant galaxies, we realize that that spectrum looks like this. The wavelengths are shifted towards red, which should have been in the original position as our sun. So based on this idea, we reach to this conclusion that if these galaxies are moving away from us because of the Doppler effect, then there must have been a time when they were close together, when they were collected at a single point. Now, we are observing everything from the Earth. It is possible that we are also moving away from another galaxy that is slightly behind us or slightly in 3 dimension is located somewhere else. So in reality, in truth, everything, every single object is moving away from each other in terms of the expansion of the universe. This gives rise to another logic that if everything's expanding, then that means that before this expansion or this explosion took place, there must have been a time when everything was placed together in a single mass, when everything was concentrated at a single point. Now, that is known as the Big Bang. This single point actually exploded to form our universe, and since this is an explosion, everything is moving away from each other. That is the idea of the Big Bang theory, right? It's all based on conclusion and continuation and theories that if everything is moving away from each other today, then they must have been together at a point in past, in the previous lifetime, right? Okay. So we understand the use of this equation as well. We understand that redshift leads to the idea of the expanding universe and the Big Bang theory. The last is the Hubble's law. Let's move towards Hubble's law. What is that? Now, Hubble's law suggests that the velocity of receding, the speed at which the galaxy is moving away from you, is proportional to its distance. If the galaxy is far away from you, then it is very likely that its speed moving away from you is also higher. What does that mean in terms of statement? Let's say that the distance of this galaxy, I'm putting it into smaller values, is 10 kilometers. Then the speed of recession of this galaxy, let's say for the sake of example, is 500 meters per second. If I can compare this with another galaxy, let's say that this galaxy is approximately 30 kilometers away. It is much farther away from me than the galaxy 1. This will be moving at a speed of, let's say, 750 meters per second. So as you move away, as the galaxies are moving away from you, they are accelerating, their velocities are increasing. And if the galaxy is further away, if it is high distance from you, from Earth, it is very likely that its speed will be greater in comparison to another galaxy, which is much closer to you. This is Hubble's law, right? So if the distance is higher, then its speed of recession, speed of moving away from you will also be greater. And of course, making this into an equation, this is the Hubble's constant, which has this value. Now, when you compare and when we read this data from the galaxies that we can read conveniently the data from that are close to us, this is the graph that we get. So this is the velocity corner, this is a distance corner, and we can see a general trend. It's possible that this is another galaxy, this is another galaxy, it's very possible. But the general trend from all these data points gives rise to this single idea that velocity is proportional to distance, right? Okay, so then we make this constant line that covers all the points, so the line of best fit, and you can see that the gradient of this equation is basically the Hubble's constant. Anyways, moving on from the Hubble's equation, this is all the contribution Hubble's has in this idea. Let's move on to the questions. He says, state the Hubble's law and identify any symbols that you're using. You see, you have to mention that speed is directly proportional to the distance. But you will only get 1 mark for this. You have to mention speed of recession of the galaxy is proportional to the distance of galaxy from the Earth. From Earth. That is how you get full marks. And you can go back to this paper and check out the answer and just memorize it for the Hubble's law. Okay. And if you are using, or if you are representing this in the form of an equation, let's say V is equal to H naught D, then you still have to explain all these symbols in a statement form. What I generally recommend is write down the statement and then write down the formula. Okay. Let's move on to question number 10, taken from February-March 2023, paper 4.2. He says that a spectral line is observed to have a wavelength of 660. The actual wavelength is 656. And just to put it into plain perspective, you see, the wavelength observed at the Earth will always be smaller number. And the wavelength observed from a distant star will always be a greater number because they are all shifting towards a larger value. Or you can say they are getting closer to wavelength of the red color. That's why we call this red shift. So no need to worry about subtracting this value from this value. This is your true value, 656. This is what you should have gotten. So again, employing the formula, change in lambda divided by lambda is approximately equal to V divided by C. Now, one more thing to be noticed over here. Do we need to deal with this nanometer over here? We don't need to do that because in the numerator we have nanometer, in the denominator we have nanometer. So it's going to be a very simple and straightforward equation. So this is going to be 660 minus 656.3. Let's look at the full values. This is 660.9 minus 656.3 divided by 656.3, which is approximately equal to V divided by speed of light, which is 3 into 10 raised to power 8. When you calculate this, your velocity is going to come out as 2.1 into 10 raised to power 6 meters per second, which means that this galaxy is moving away from us at a speed of 2.1 into 10 raised to power 6, which is a very high speed. He says now calculate the distance from the star or up to the star if the Hubble constant is this. Again, we use the equation of Hubble's law, which is V equals to H naught D. We found the speed of recession to be 2.1 into 10 raised to power 6. Hubble constant is T.3 into 10 raised to power minus 18, and distance can be found easily. So D in this situation comes out as 9.1 into 10 raised to power 23 meters. You can write this down over here. The third part is interesting, and you should memorize the answer to this question. He says, state and explain what can be concluded about the universe based on the change in the observed wavelength. He says that the wavelength is changing. It changed from 656 to 660. What can you say about that? So you have to involve Doppler effect. You have to involve the expansion of the universe. So wavelength has increased. Why has it increased? Because of the Doppler effect. Where do we find the evidence for that? Doppler effect, which means the stars and galaxies are moving away from each other, receding from the Earth, and hence we can conclude that the universe is ever expanding, right? A memorized, or you can say a very basic and standard answer for this question. Question number 10 from May 23, paper 4.3. In this part, there is one value that is missing. The distance of galaxy is mentioned or is found to be in previous part to be 1.8 into 10 raised to power 24 meters. This will help us in second part. Okay. He says, explain why the wavelength observed on the Earth is different from the wavelength that is galaxy known has emitted. Again, it is going to give you the same answer that we found in the previous part. Okay, you can go back to the question and memorize the marking scheme because the galaxies are moving away from each other and the Doppler effect produces or causes the wavelengths to increase and get closer to the red side of the spectrum. Determine the value of the Hubble constant. So first, notice that this is a 3-mark question, so it's going to require at least more than one steps. We have 486, we have 492. And again, just look at the wavelengths. And as I've told you, that the wavelength observed on the Earth of the sun, of our own sun, will be smaller. And the wavelength coming from a distant galaxy is going to be larger. So this is coming from the galaxy. And 486 is from our own sun, plain and simple. So change in wavelength divided by original wavelength is approximately equal to V divided by C. This is V divided by C, and V is the speed of recession. Let's write down the values over here. So this is going to be 492 minus 486 divided by 486, approximately equal to V divided by 3 into 10 raised to power 8. So we found the speed to be 3.7 into 10 raised to power 6 meters per second of the galaxy. The galaxy is moving away from us at a speed of 3.7 power 6. Then we use Hubble's equation, V equals to H naught D. So this is 3.7 into 10 raised to power 6. H naught is what we don't know. We want to find out. And the distance was found in the previous part of this past paper. You can go back and check question number 10 as 1.8 into 10 to the power 24 meters. So when we find h naught, this comes out as 2.1 into 10 to the power minus 18 per second. We're going to write this down over here, and we are done with these questions. So these are the type of questions you can expect from this topic, and I hope that we understand all the points highlighted in the syllabus. That is all for today.